Okay, vocal check 1, 2, 3. Good morning, Cisco cohort 2. And before we start today, I just wanted to show you again this coming up this Thursday at 12 o'clock noon is a Texas Network Academy Career Fair webinar. And there's a link on the bottom of my TCC Blackboard where you can click and go to click on this to register. They'll send you a link to join the webinar when it starts live. So there's going to be actual hiring employers from the Dallas-Fort Worth area. They're looking for people that know something about Cisco. Now, on today, what we're going to look at is, let me see, click on this and click on this. And there was a slight error in the syllabus. It said chapter 5 and 6 today. It's actually 6 and 7. 6 will cover the data link layer, and then 7 will look at Ethernet switching. And we're taping, we're recording, and we're sharing. Okay, so the first module we're looking at today is module 6, the data link layer. And we're going to look at what is this for? What is a data link layer for? The data link layer was our layer 2 of the OSI 7-layer reference model. And it was basically where things like Ethernet live. And then we're going to look at a little bit more detail about how Ethernet specifically operates, because Ethernet is the predominantly most popular type of technology used today for this type of networking. Look at topologies like local area networks and wide area networks, and then we'll look at the data link layer frame, and then later on we'll get into more detail about Ethernet frames, which is the one we're going to be using most of the time. So what's the purpose of the data link layer? When the engineers got together at the OSI, the International Standard Organization, and came up with a 7-layer model, they were criticized later by the IEEE that says it should have been 8 layers and not 7 layers. The reason being, all the upper layers are software layers, or lines of code that run in computers and routers and switches and things of that sort. And the bottom layers are they're hardware, wires, network interface cards, things of that nature. So the IEEE engineers said, well, you know, when you go to Fry's, well, I guess you can't go to Fry's anymore, and buy a Ethernet adapter, you get 2 things in the box. You get a USB attached, your PCI attached Ethernet adapter you can plug into your computer, which is a hardware. And then you get a software portion. You get a device driver disk with the drivers for Windows and the driver for Macintosh and the drivers for Novell Network and the drivers for Windows Server and things of that nature. So the data link layer is kind of like a shim that ties in the hardware to the software. All the upper layer protocols that we're using, and we used to use lots of many very different types of upper layer protocols like AppleTalk and Novell Network, IPX, SPX, and IBM SNA mainframe stuff. But these days, the trend is everything over IP. So IP version 4, the legacy version of IPv4, and IP version 6, the later version of IP that has more bits in it so that we can not run out of network addresses. It takes these upper layer protocols and takes this IP version 4 and IP version 6, which is a pure software packet at the network layer, and encapsulates it into a layer 2 frame, which eventually is going to be turned into bits and shot out over the media. And it also has the job any type of error detection or bad frames. There's a frame check sequence redundancy, frame check sequence mechanism built into data link layer frames that can make sure that some physical layer problem like electrical interference messes up the bits of a frame, that we can tell that happened and we can throw the frame away because we now know it contains bad information. So the IEEE guys are the ones that stepped in and said, look at this data link layer, which is sort of the term, my pencil here, sort of in purple here. Here's the data link layer. And the IEEE guys certainly upheld the Hicks rule of engineers, which says that the only thing that 2 engineers will ever agree upon is that that 3rd engineer is wrong. So the IEEE engineers said, those OSI guys should have divided that data link layer into the hardware portion and the software portion. So the software portion is the logical link control sublayer. And that's where the device driver software driver disk exists. So when you buy a network adapter, you get the hardware portion, but you also get a software portion. Now, sometimes they don't give it to you in the box, you have to download it. Or if you're using Windows 10, it usually has it built right in. So that's a software shim that takes the software that's coming down from the upper layers, which eventually it's going to be an IP packet at the network layer. And it adapts that to the peculiarities of the actual hardware that's in that particular device. You know, is it a 3Com network card? Is it a Dell network card? Whatever brand of network card it is, it will make sure that that device shims into the Windows operating system going up and down to the specific hardware that comprises that network interface adapter going on downwards. So the logical link control is that software. Now the hardware itself is, the hardware starts here and goes all the way down here to the physical layer. So here we have our network interface adapter, a real piece of copper printed circuit board. Has the RJ45 connector on it, plugs into the wire. And it has this, it's called the media access controller, MAC layer. That's where the term MAC address comes from. The MAC address is a physical burn-in address in that Ethernet device. And then we can have various forms of Ethernet. He mentions 802.3 Ethernet, which is your regular standard wired Ethernet with an RJ45 connector. We have 802.11 for various types of Wi-Fi that use radio frequency energy instead of physical copper wires. And then we have IEEE 802.15, which is for things like Bluetooth, things of that nature. So packets that are going between nodes would go through various media transitions. They go through various link layers. So let's say that there's 3 routers between you and the website that you're looking at. There's usually more like 10 or 15. There's a certain number of routers at your home. You have your home router that's at your ISP. You have your ISP router that takes your traffic. And then it's got to go to backbone carriers and then eventually to whatever website you're trying to get to their web pages for. So at every time we go between 2 routers here, the router has got to do these 4 basic things. He's got to accept the frame from the network media. He's got to read in the bits from the network media, which could be a twisted copper cable, could be flashes of light on a fiber optic cable, could be radio frequency energy pulses going through the air. He accepts all those bits and puts them together into a network frame. He's going to check that frame to make sure he hasn't any errors in it. There's a mechanism at the end of the frame called the frame check sequence of the CRC that's going to check and make sure that none of the bits got horribly scrambled up as it was going along the network medium. Then he's going to take that frame, he's going to open up that network frame, that Ethernet frame probably, and he's going to open up that Ethernet frame and pull out an IP packet, and maybe IP version 4 packet or an IP version 6 packet. And he's going to make the forwarding decision. If it's a router, he will look in his routing table, he will make the forwarding decision. He'll take that packet that he took out of the frame, he received it on interface A, and he'll re-encapsulate it into a new frame, a new data link layer frame on interface B. Maybe another Ethernet frame, maybe a serial frame. These days, everything is mostly over Ethernet. We don't have so much serial point-to-point protocol stuff anymore. But he's going to re-encapsulate that frame, that packet, into a new frame, and then forward that frame out that second interface, interface B, onto the second wire. So it'll be on its way. So at each step along this process, the upper layer data, the IP addresses, they don't change at all. Any more than when you put a letter in the mail, they don't scratch your address out and put routing information on the envelope itself. But the data link layer information keeps changing. So if the MAC address of your PC that when you click send and you send information, the source address is the MAC address of your PC. Once it goes into that first router and goes out to interface B of that second router, it gets a new MAC address, whatever the physical burned-in Ethernet MAC address of that second device was. So that information constantly changes. Layer 2 addresses, source and destination addresses change constantly from link to link as the The packet itself moves along the path. The packet itself, like the mail in the mailman's leather bag and in the mailman's truck and in the plane, it doesn't get changed any. There are some different organizations that are responsible or have set up some protocol standards. So the IEEE is the International Organization of Electrical and Electronic Engineers, like college students and professionals that are working in electronics. We mentioned some of these standards before in an earlier thing. The International Telecommunication Union, ITU, used to be CCITT. That makes all the telephones work with each other so that you can make a call from any country to any other country, and the billing can be done properly. The ISO, they're the people that came up with the dreaded, feared, and hated OSI 7-layer reference model. And then the American National Standards Institute are some standards organizations that participate in this because it's in the best interest for business and commerce to be standardization. So when you buy a nut and a bolt, they're going to fit together with each other. For example, if you're building cars, the nuts and the bolts have to have the right threads in them, or you can't build cars. So in networking, we have to have these standards or we can't communicate with each other. Now let's look at some topologies. So physical topologies and logical topologies. So packet tracer. Packet tracer has a logical topology mode. It's a default mode when you start packet tracer, and you see a diagram at the top that looks sort of like, you know, the graphical drawing that's on top of every one of the labs that we do. It'll show a router and a switch and two PCs and how they plug together, and just logically how they're connected together. It has no relationship with physically what room they're in or physically what type of wire was used to plug them together with. And when you kick in the new physical topology mode of packet tracer, you can actually physically, you know, I'm putting this router in this rack, I'm putting this switch in this rack, I'm putting this PCA and this BCB on top of this desk. And it's more like a blueprint for a building. It shows exactly where the devices are and how they're interconnected. Wide area network. Let's review again. What is a wide area network? Well, we have local area networks, which are within a building, and they usually have a distance limitation of the 328 feet that a copper cable can go. So in most buildings, they place a wiring closet somewhere in the center of the building, and it's less than 300 feet to the corners of all the buildings, so they can wire and plug together. Just like in our classroom building, we have our hundreds of devices all plugged together into a wiring closet that's almost in the center of the building. Wide area network technologies are used when you have a LAN at the South Campus and a LAN at the Northeast Campus and a LAN at the Southeast Campus, and we need to connect them together. We don't have the right to dig ditches along the highway and put in our own fiber optic cable and connect these campuses together. So you have to go to a common carrier, a service provider, and you can lease WANs from them. So wide area networks connect local area networks together using a technology that's good for more than 328 feet. You know, it's 18 miles between South Campus and Northeast Campus. So we lease a link from them. We're leasing a technology from the telephone company called Gigabit Ethernet technology that connects them together. They use a proprietary internal technology, and they present a Gigabit Ethernet plug to us at the South Campus and a Gigabit Ethernet RJ45 plug to the Northeast Campus, so we can just plug our two campuses together that way, just like plugging a PC into a switch. Three types of common WAN topologies is point-to-point. Think of if there was just a Southeast Campus and the Northeast Campus, it'd be a point-to-point connection between the both of them. We'd lease a permanent link between them. But TCC is more than one campus. So we have a hub. We have our downtown Trinity River campus. And then we have all our campuses in the Northwest Campus and the Northeast Campus and the South Campus and the Southeast Campus. And we have several other centers like our airport training stuff. That's a hub and spoke. So the hub is the middle of the wheel, and like a wagon wheel or like a spider web, the spokes are the lines that go out to each individual location. So Tarrant County College uses a hub and spoke technology where Trinity River is the center. And then the spokes go out to all the individual campuses. And then Trinity River has the master connection to all the campuses and the connection to our CenturyLink link up to the internet service provider that we use. Now the third one is the most expensive, but it's the most reliable. Fault tolerance is like a RAID drive array. If one drive fails, you don't lose any of your data. Or a UPS, if the commercial power fails, the battery keeps running the computer. So in a mesh topology, very high availability. Instead of just one connection between downtown campus to south and one connection between downtown campus to northeast, we have additional connections, like a direct connection between south campus and the northeast campus. So the advantage of mesh is that if any one link fails, then we still have connectivity. We can use an alternate backup route. But it is, on the downside, it's more expensive because we have to provision and pay for on a monthly recurring basis forever the links of all these additional lines. So a typical point-to-point WAN topology would be two offices, and let's say that the one on the left is in Fort Worth and the one on the right is in Dallas. So we can't dig our own ditch along the old Dallas-Fort Worth Turnpike and put our wire in. We're going to lease a connection between Dallas and Fort Worth from a service provider. We can use the phone company, or there's several companies that offer these services. And a physical point-to-point topology would then connect these two nodes together. Since it's a simple point-to-point topology, there's really not that much of a question of identity. Now, when we have a room full of 24 students in a classroom, we have to look at the 48-bit physical MAC addresses of each one of the computers to tell them apart. But in the simple leased link between two locations, there's just the router on the left in Fort Worth and the router on the right that's in Dallas. So the protocol can be very simple. It's anything that this node sends out, node 2 will hear. Anything that node 1 sends back to the west, to Fort Worth will hear it. So in WAN topologies, the identification is essentially it's 8 ones. It doesn't matter. Anything you say, I hear. Anything I say, you hear. LAN topologies are, the original ones were a bus topology. The original LAN topologies were, there was a big, thick Ethernet cable that went through the building, and every room that we had PCs in, we would attach a vampire tap to that wire, and all those rooms would be connected to each other. IBM had a topology called ring topology. They had a technology called token ring, and all the workstations were connected into a circle. And the ring topology, there was no collisions because there was only one device that was allowed to transmit data at one particular time. They would pass a token from host machine to host machine, and you could only transmit data when the token came around to you. But these days, overwhelmingly, we're using a star topology. So in our classroom building, we have all the computers in the building connected to it. This little center of the star, that's the wiring closet that's out in the hallway, and it's got 12 or 13 Ethernet switches, 48-port Ethernet switches on it that connect all the devices on our floor together. And that's the point. That's a hub and spoke. Star is hub and spoke, same thing. We call it hub and spoke when it's WAN. We call it star when it's a local area network. Now imagine we have the downstairs of the business building, and we have our wiring closet on the first floor. Upstairs, where the accounting and financial department is, they have their own wiring closet, and the two wiring closets are connected with a fiber optic cable between them. And then we can extend this star topology to all the buildings on campus. So, as he points out, fairly easy to install, easy to troubleshoot for us technicians and engineers who have to get these things up and running and keep them running and fix them. And very scalable. If I want to add another floor of a building, I just, add another wiring closet and spoke out and add that. So when we added the new air conditioning building on the other side of campus, we just extended the wire over to that campus and plugged all those devices in. Half in duplex, half and full duplex communication. I'll use the allegory here of telephones are full duplex communications. When you pick up a telephone and I'm talking to you, you can interrupt me and I can hear you while I'm speaking. Modern Ethernet switches operate in the full duplex mode. They can send and receive at the same time. Half duplex communication is like the CB radios or taxi cab radios or police radios. They push down on their button, on their microphone button, and while you're talking on the CB radio with your button held down, you can't hear anybody. Nobody can interrupt you. They can't say, hold on, you're breaking up, send it again. You got to wait till you let go of the microphone, and then they can tell you. So half duplex is like the old Ethernet hubs. Only one device could transmit at a time. And while he was transmitting, he couldn't hear anything. So this is only used on the legacy. Whenever you see the word legacy, whenever I say legacy, you will think old, obsolete, shouldn't be used anymore, it should be thrown away, and we should get some new technology if it weren't so cheap. So some enterprises are kind of cheap. Lawyers and doctors, they charge a lot of money, but for some reason they're real cheap with their equipment. They use the oldest technology and they don't want to upgrade. Wireless LANs, the older wireless LANs access points use a single shared channel. Now some of the newer wire LANs are more like an Ethernet switch. They have, you've seen the wireless routers that have like 3 antennas sticking out of them, MIMO type technology. They can transmit on several different channels at the same time. So they operate more like an Ethernet switch than an Ethernet hub. The methods of getting access to the system, the old contention-based system, and this is what I call the Three Stooges poking each other's eyes out. You can transmit whenever you feel like it, but you're supposed to listen first and see if anyone else is using the media before you try to transmit. So the old party lines that the farmers used in the country, it was one telephone number shared among 8 farmers. And if Farmer Jones picked up the phone and he heard Farmer Smith's wife talking, he didn't get a dial tone. He had to hang up and try again. There couldn't be 2 conversations at the same time. So in the old hub-based Ethernet systems, this was like this. Only one device could transmit at the same time. All the other devices, if they wanted to transmit, they would listen and hear bits being transmitted. Uh-oh, Farmer Smith's wife is talking. They can't transmit. They have to wait till that's over. So contention-based access uses a carrier sense multiple access collision detection scheme, which means that I can hear other people's traffic, and if by chance 2 host machines just happen to start transmitting, they both listened, heard silence, and they said, it's okay for me to transmit, I hear silence, and they both just started transmitting at about the same moment in time, they would create an Ethernet collision, and then the Ethernet collision would be sensed, collision detection, and they would both stop and start a random timer and start all over again. Now, Wi-Fi uses an advanced scheme that they stole from Apple Talk, Local Talk, which is if I intend to transmit, I'm going to listen for the silence, and if I hear the silence, I'm going to send out a little pulse that says, I intend to transmit, everybody else keep quiet because I have taken possession of the line, I've seized the channel, you be quiet until I finish doing it. And that reduces the collision somewhat in an environment that's really subject to collisions, like a shared radio channel, like a Wi-Fi channel. So Wi-Fi uses carrier sense multiple access collision avoidance to further reduce. There's still going to be some collisions, but it'll reduce them some more. Now the old ArcNet and token ring systems, this used a special token frame, and the token frame circulated around in a circle around all the host machines. And if any host machine had data he wished to transmit, he would take the token and he would expand it out and make it a data frame, and he would put his data on it. It would travel around the circle till it got to the receiving workstation. The receiving workstation would accept the data and then shrink the data frame back to a token frame, and the token frame would be placed back in circulation. So there can't be any collisions. It's controlled access. It's deterministic. So let's see, to make a religious joke about this, the Methodists have free choice. You can determine what you want to do, but the Presbyterians, they believe in deterministic. Your fate is already decided. So token ring is controlled access. Ethernet is contention-based. So the scheme used is carrier sense multiple access collision detection, which is used by legacy Ethernet local area networks. We still use it. It's still, the code is still running for this on our host machines, but when we use a modern switch instead of a hub, there's not going to be collisions because we have microsegmentation to the desktop. We have our own private collision domain from port 6 of switch 1 to our PCA. It's not being shared by anything else, so there can't be any collisions. So one device can send and receive at a time, and he can use the full duplex mode. He can actually send and receive at the same time. So here's the way that the detection process starts. If 2 devices happen to transmit at exactly the same moment in time, because they both waited and they heard silence, and they both start transmitting their bits at exactly the same time, then we're going to hear a collision. And the collision is going to be, it's this. In binary, we have one electrical level that represents the bit 0, and we have one binary level that represents the bit 1. And if we send the electrical zeros and ones out on the wire, okay, well, voltage, this voltage is a 0, this voltage is a 1. If two devices get on the wire at the same time and start to create the collision, there's going to be some ones and zeros occurring simultaneously, and the voltages will add up to more than just a 0 or 1. Well, in binary, there's only 0 and 1. There's no 2 and 3 and 4. So the wires here, 2, 3s, and 4s, added voltages together. If you put multiple voltages electrically on a wire, they add up together. So the devices detect the collision. They hear something that's not a valid 1 or a 0, and they know a collision has occurred, and each host machine, each device turns on a random timer and waits for that random timer to run out. And when the random timer runs out, he again listens to the wire, waits for silence, and attempts to retransmit his data. So that's how Ethernet worked with the old hub-based systems where devices could collide with each other. And I had a lot of experience with this back in the 90s when I worked for a college textbook publisher in downtown Fort Worth, and we had 250 people sharing a single shared Ethernet hubs that were chained together. Collision light was always on. So carrier sense multiple access collision avoidance is used by wireless LANs like Wi-Fi. It's half duplex. It's like the old Ethernet hubs. It uses the collision detection, but it also has a collision avoidance, which is like sending out a special little ping or a pulse when each station listens to the media and he doesn't hear any radio frequency energy. There's an absence of bits, means the channel is clear and he should be able to transmit his data. So he sends out a special signal saying, clear the channel, radio silence, I intend to transmit myself. So that reduces the collisions a little bit more. Now we're looking to look at the data link layer frame. Data link layer frame has a header, which contains some addressing information. We'll look at it in a little bit more in detail. Has the actual upper layer data, the upper layer encapsulated data, like maybe an IP packet. And then at the end, it has a trailer. This trailer information is a frame check sequence, a cyclic redundancy checksum type code that checks to make sure that the entire frame, that none of the bits got scrambled up when it was being transmitted across the wire, because electrical interference or radio frequency interference could corrupt the data. So this varies according to the technology and the speed of the Ethernet and so forth. So generically, they're going to look like this. Every frame is going to have a header, and this header is going to have a start of frame delimiter that tells us this is the beginning of the frame. It's going to contain some addressing information in the Ethernet frame. That's going to be the source and destination MAC addresses. A type or control field, which is used to indicate what type of upper layer data is encapsulated in this Ethernet frame. Could be an IP version 4 packet, could be an IP version 6 packet, could be a ping request. It needs to know that. Then we have our upper layer data itself. The actual IP version 4 or IP version 6 packet is the data portion of the frame. And at the end, there is a cyclic redundancy checksum CRC-based frame check sequence at the end that checks to make sure that the data is okay. And he's going to do this by taking the start of the frame and going all the way to the end of the frame and generating a binary 32-bit sort of a checksum of the contents of the data, and he'll transmit that along with the frame. And then when the receiving workstation receives the entire frame, he will recalculate the error detection, the CRC, the frame check sequence, and it should match. If it doesn't match what he calculated, that's how the receiving workstation can detect that the frame has become corrupted, and he'll simply discard the frame. Eventually, some upper layer protocol like TCP, positive acknowledgement and retransmission, he will retransmit that frame again. So layer 2 addresses, MAC addresses, physical addresses, burned-in addresses. This is contained in the frame header, and it's only locally significant only. So here we have our original source host machine, and he needs to transmit something to the first router hop. It's only going to be the layer 2 addresses along that link. It's only for local delivery of that frame on the link. Once that packet that this layer 3 packet that this guy created, once it goes through router number 1 and gets assigned to an exit interface, the layer 3 packet itself is not changed. But now he's got a new MAC address because this Ethernet port has got a different MAC address than the other Ethernet port it came from. So they get these constantly changing, locally significant only, local delivery importance only, layer 2 network, layer 2 data link layer addresses as it goes from point to point. But the packet itself, the gray layer 3 packet itself, is not altered in any sense. So the purple addresses keep changing from link to link. In this case, in this diagram, we have 1, 2, 3 sets of data link layer addresses, source and destination network addresses, as this request from this user with the purple shirt on his desktop host client PC is requesting something from the data server over on the right-hand side. So local area network and wide area network frames are, at the CCNA level, we used to pay a lot of attention to point-to-point protocol and high-level data link control and frame relay, and when you use serial ports, and that's been de-emphasized now. We're not going to be configuring these anymore. We're going to simply look at this from the 90,000 feet stratospheric level, but we're not going to be down on the tarmac and actually work on them. We're going to just work on the Ethernet standards. Ethernet over twisted pair cable, or Ethernet over fiber optic, or Ethernet over radio waves like 802.11 Wi-Fi wireless. So each protocol, depending on which one you use, performs some type of media access control. When do I get to send my bits out over the wire so that I can encapsulate my data and send it back and forth? Okay, now I think we need to go to share the file, share the file. So overwhelmingly today, Ethernet is used pretty much, it's been used for local area networks all the time. We used to use serial ports like point-to-point protocol and frame relay and stuff to connect our different locations together through our hard WAN circuits like T1 lines. But these days, Ethernet handoff technology has become more popular. It's pretty much taken over the market, really. And so it's Ethernet everywhere. And this makes it easier for us, so we don't have to set up a weird serial protocol to connect the Dallas office to the Fort Worth office. We'll just get a little box from our carrier that we lease the circuit from. It'll have an RJ45 on it. And we don't have to run a serial cable and DCE and DTE and all this other confusing stuff. We just plug the serial cable. We just plug the Ethernet cable to the RJ45 of the box the carrier gave us, and we plug it into our router at our facility, just like you do at home. You get a cable modem or a DSL telephone modem, has an RJ45 connector. It puts out Ethernet. You plug that Ethernet cable from that device into your home router, and you're connected to your internet service provider. So we'll look at how Ethernet sublayers are related to frame fields. We're going to look a little bit about the MAC address, that burned-in physical address that's in each Ethernet device. We're going to look at switches. Switches are these devices, these 24-port devices we plug a bunch of PCs into so they can all talk on the network. And we'll explain how the switch works logically. Switches have a lot of sophisticated intelligence. They're not like the dumb hubs. The dumb hubs are just repeated everything. Don't be in the hub club. Don't be dumb. Be in the switch club. Be smart. Be intelligent. And we'll look at the process for how switches determine how they forward frames back and forth, and some of the tricks that some of the Cisco engineers and other switch manufacturers have done to speed up this process. If you want to get really fast performance, they have some tricks up their sleeves for this. Okay, so Ethernet frame. We had our standard frame. Now let's look at an Ethernet frame. First of all, let's look at this encapsulation. So the dreaded, feared-and-hated OSI 7-layer reference model had the data link, but the IEEE engineer says, no, 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 it really should have been 8 layers, because the lower layer is the physical, the media access control is the physical part, like the network adapter itself that you plug in. And the logical link control is the lines of software that go into the Windows 10 device driver that shim that hardware up to the software. So the Ethernet standard 802.3 for Ethernet is really 1.5 layers. It's physical. The entire physical layer is physical wires and plugs, printed circuit boards. And then the bottom half of the data link layer is the burned-in physical MAC address of that printed circuit board that you plugged into your desktop's PCI socket or a USB attached device so it could communicate on the internet. So this to me looks overly complicated, but I'm sticking with my more simplified explanation as to logical link control is software, It's device driver that comes on a disk. It's the proper device driver to go upward to the software, whether it's Windows 10 or Mac OS or Linux or whatever software is present on that. There's a different device driver for every computer operating system. And then it goes downward and actually communicates with the electrons that are running along physically on the printed circuit boards on that device that it needs to plug into. So there are some different standards because we can use wired Ethernet, we can use Wi-Fi Ethernet, we can use Bluetooth. So there's some various standards out there for adapting to the many very different types of physical technology, electronics technology, and what operating system are you using. These all got to be plugged together where they can shim into each other. So the MAC sublayer does the physical stuff. It actually takes the data, the upper layer data from, say, an IP packet that's in the software of a Windows PC, like a PC-A, and it needs to take that IP packet and it needs to encapsulate it in an Ethernet frame so it physically can be transmitted along the wire to port number 6 of that Ethernet switch is plugged into. So the Ethernet frame itself is the Ethernet frame structure. We have some addressing, which is the 48-bit MAC address. We have a source address and a destination address. If it's IP version 6, it's 128-bit addressing. IP version 4 packets are 32 bits. IP version 6 packets are 128 bits. But regardless of the addressing that takes place at the network layer, Ethernet itself is just 48-bit physical MAC addresses. And then at the end of every Ethernet frame, we have this frame check sequence, a cyclic redundancy checksum to check to make sure that none of our bits got clobbered as they went from one end of the wire to the other, and they're all the same. This is a very accurate test that can determine if the receiving workstation calculates the same CRC that he heard on the wire. That's an absolute guarantee that the data is good. So IEEE 802.3, the MAC layer is the physical layer. So we can have different kinds of physical devices, can't we? We can have twisted pair copper RJ45 cables. We can have fiber optic cables. We can have 802.11 Wi-Fi radio frequency energy. So there's lots of different ways we can transmit the bits back and forth. We need the proper device driver for that copper or that fiber or that Wi-Fi or however we're connecting stuff back and forth. So all Ethernet devices today are pretty much full duplex. This full duplex came on the scene in about 1995, about the same time that fast Ethernet came on the scene. We were all half duplex, standard slow legacy Ethernet, 10 megabit second Ethernet before then. So therefore, you really don't need carrier-sense multiple access collision detection with full duplex links because everybody's got a private highway, a private micro-segmentation to the desktop from each individual device to a single dedicated port on a switch. But what if somebody takes an old hub and plugs it into their office and plugs 3 devices together? Well, that switchboard still needs to be able to detect collisions and recover from them. So they're checking for collisions. There's just no collisions, should never occur if you have proper network design, because we shouldn't use hubs in the office again. That's bad performance. And the IT will track us down and say, you're not supposed to put foreign devices on our network. So here's Ethernet frame field. So the very beginning of Ethernet frame is a starter frame delimiter, SFD, starter frame delimiter, as a preamble. It's a alternating series of bits, alternating 0, 1, 0, 1, 0, 1, 0, 1. And it does that 30 times. And the very last repetition is 1, 1. That's a wake-up call. It's there for legacy reasons, because when the IBM PC came out in 1980 or so, and Ethernet was slow, this was a way of telling the Ethernet adapter on that old slow IBM PC. I think it ran at 3.77 megahertz clock speed. It was really, really slow. The Ethernet adapter needed a bunch of those pulses to wake them up and say, get ready, Ethernet NIC card, here comes an Ethernet frame, and you're going to have to be able to process it and send it upstairs through your logical link control device driver to the Windows or DOS operating system that's in this IBM PC. So it's there for legacy reasons now. Now we're running gigabit Ethernet and 100 gigabit Ethernet, and the devices are much faster. They don't need that wake up call, but it's there for legacy reasons because it was in there originally. And all this. Oh, by the way, every speed of Ethernet uses this exact same frame structure. Doesn't matter whether it's 10 megabit, 100 megabit fast Ethernet, gigabit Ethernet, whatever speed it is. They all use this exact same structure. Now, back in the old days when we had hubs and we had collisions, we had to set this minimum Ethernet frame size to 64 bytes because if it was any smaller than that, it could be confused as a collision fragment. And we had to set a maximum size of 1,518 bytes so that you could just take over the network wire and use it indefinitely to transmit your War and Peace 400 pages document to the printer, and nobody else had to wait for the printer to print it. Any frame less than 64 bytes is considered a RET and maybe a collision fragment. It's thrown away, it's discarded. Frames with more than 1,500 bytes or characters of data, they're considered jumbo or baby giant frames. And in some network attached storage or it's dyslexic neighbor storage attached networks, they do use some giant frame stuff like 10,000 byte frames to try to get more efficiency in their giant banks of hard disk drives that are shared among the entire enterprise. But typically at the CCNA level, no, we're going to stick to this 1,500 characters of data and say that the maximum size of an Ethernet frame is 1,518 bytes, and we'll only break that rule in the next 8 weeks when we talk about VLAN tagging. Now, if the size of a transmitted frame is less than a minimum or greater than a maximum, it should be dropped, probably because of a collision, electrical interference. So this preamble is wake up, here comes the stuff. The next portion is, what is the destination address that this Ethernet frame is being addressed to? Well, your PCA, it would be your home machine, it would be the 192.168.1.1 IP address, whatever MAC address that has physically of your home router, because he's going to send it to the ISP and determine the best path. It's at the very front of the frame, and we'll see later that you can do some lookup processes more quickly because it's given to us first. After that is the source MAC address. Now, you notice it says 6 bytes. How many bits are in a byte? Let's see, go back to our Computers for Terrified Adults class. Oh yeah, there's 8 bits in a byte, and let's go to 3rd grade math. 8 times 6 is 48, so 48 bits in a MAC address, 6 bytes. Then we have a type length field. This tells us what kind of upper layer data is being encapsulated in this Ethernet frame. And in the CCNA level, it's going to be an IP version 4 packet, or an IP version 6 packet, or maybe a ping request. Then we have our actual upper layer data itself, the actual IP packet. And then at the end, 4 bytes. Well, let's see, 4 times 8 is 32. It's CRC32 is the protocol used. Cyclic redundancy checksum 32 is a frame check sequence. And the device that transmits this data is going to take the unique data composing that frame up to this point and run a calculation on that based upon the bits, the ones and zeros, and come up with a unique 32-bit frame check sequence or CRC. He's going to transmit that with everything else. When the receiving workstation receives this data, he's going to do the same thing again. He's going to check the data that he heard on the wire, and then he's going to take note of what he heard on the wire, what the 32 bits he heard on the wire for the frame check sequence, and he's going to recalculate it. And what he recalculates should match what he heard on the wire. If that is the case, the data is good. If they don't match, the data is bogus and it's thrown away. So Ethernet MAC addresses, 48-bit binary value. This is kind of a big value. Now with 32-bit IP version 4 addresses, we use the dotted decimal because you'll get a headache looking at binary ones and zeros. It's very difficult to look at them and compare them. So with 32-bit dotted decimal, we use the 192.168.1.1 type format. Anything bigger than that, 48-bit MAC addresses, 128-bit IP version 4 addresses, we use hexadecimal, which is the hexadecimal base 16 number system, uses the 0, 1 through 9, and then we need a single character to denote what in decimal would be 10, 11, 12, 13, 14, and 15. So we use A, B, C, D, and F for that. So if you type ipconfig/all on your Windows desktop machine, it'll show you the hexadecimal, all those 48 binary bits represented as 12 hex digits, and you'll probably see some A, B, C, D, E's, and F's in there. Now, programmers will use the 0x to denote this as a hexadecimal value instead of a decimal value. Sometimes they'll also do subscript like base 16, or they'll put an H after it. Now, in IP version 6, we had a rule that we could drop a bunch of extra zeros to try to make reduce the number of numbers in the hexadecimal digit field. But when we use hex to denote MAC addresses, we always put all the zeros in there to make it clear that it's a 48-bit binary address. Let's look at a more detail of this 48-bit binary number and how do you get to use it. Can you just make up your own number and make devices? Because this is a 48-bit value that's burned into a read-only memory chip of every Ethernet NIC adapter that's out there. And, well, no, you can't just make it whenever you want to. Can you just use any IP address you want to? No, you have to get it from your ISP, or you have to go to the name and number authority like IANA and get an address range assigned to you to use that in that. So when they came up with a scheme for 48-bit MAC addresses for Ethernet devices, they took an organization that will coordinate all of these possible addresses and hand them out to manufacturers and vendors to use. And it's the IEEE, the same guys that said, oh, you OSI guys, you're so stupid. It should be an 8-layer OSI model instead of a 7-layer OSI model. We won't even further confuse all the fundamentals networking students that will come in the future. So it's divided into 2 equal chunks. The very left portion, the first 24 bits of a MAC address, is assigned to the vendor or the manufacturer that makes the devices. So someone like Cisco, who makes a lot of devices that have Ethernet interfaces, or someone like 3Com that makes lots of PC network adapters you can plug into your PC to connect to a network. You can go to the IEEE and pay them $1,500, because we got to keep the riffraff out. And they will give you your own unique, organizational unique identifier. So how many of those can there be? Well, we have 24 bits, to the power 24, and that's like 8 billion or something like that. It's a very large number. So you pay the IEEE $1,500, and you can go into business and make your own devices that have Ethernet adapters in them, NICs in them. The remaining 24 bits, let's say I go to the IEEE and give them $1,500. How many NICs can I make before I have to go back and pay them another $1,500 and make another 8 billion? Well, I have 24 bits on the right-hand side, so whatever 2 to the power 24 is, that would be as many devices as I can make before I can go back and give another prefix. So Cisco and 3Com and Dell and other big companies have more than one prefix. This is the feature that allows programs like Wireshark, that sniffer type program that you can get for free, that's open source. When you do a Wireshark trace and it goes down to the DID link level, it'll look at those first 24 bits and it'll look up the manufacturer. So it'll tell you, oh, this is a Cisco router on this side and this is a Dell computer on this side. So divide into 2 pieces. Okay, he's talking about frame processing. When a device is forwarding a message, the Ethernet header is going to include the source MAC address of the device that created it and a destination MAC address that's is the intended recipient of the data. When a network interface card receives an Ethernet frame, he looks at the destination address and sees if it matches his own address. So in this case, the workstation has sent out, H1 has sent out a message to H3, and H1 source address is all A's and H3 source address is all C's. And H3 will recognize that 48-bit binary pattern. He says, well, that's my pattern. I must accept this data and send it on up to my operating system. But workstations H2 and H4, host machines H2 and H4, they have a different MAC address. They're going to listen to it. They need to listen to all the data to determine if they need to send it up to their operating system. But they'll say, that's not my address. That's not my destination address. I'm going to ignore it. Now, there is a note here that there's a special thing called a broadcast group or multicast group in which they will pay attention to a value that's not particularly there. So, for example, an ARP request is in the form of a broadcast, because an ARP request is a way I say I'm PCH1 and I'm trying to ping PCH3, but I don't have that in my ARP cache, so I'm sending out a ARP request that says, calling all stations, if your MAC address, if your IP address is the IP address of H3, please send me back your MAC address because I want to be able to ping you. I need to know your MAC address to encapsulate that ping request in the Ethernet frame. So it's heard by all of them. Workstations H2 and H4 hear the broadcast, and they're compelled to unencapsulate and send all broadcasts up to the operating system, and the operating system will say, well, that's not my IP address. I don't need to do this. I can just ignore this. So what type of devices will have MAC addresses? PCAs and PCBs, workstations that students or employees use in a company. So desktop PCs, laptop PCs, servers, printers, mobile devices like tablets, telephones. These all have MAC addresses, and routers and switches. They all have to have MAC addresses to operate on the network. So let's look at unicast. We talked about unicast and multicast and broadcast before. So the unicast is a one-to-one communication. In this case, the source host, H1, is sending a message directly to the server. So it's a one-to-one communication between the 192.168.1.5 address of the first host to the 192.168.1.2 address of that server. So a unicast MAC address, here's the source address of this workstation, here's the source address of the server he's trying to communicate with. Unicast is one-to-one. So just like in IP, he's going to send a unicast IP address and a unicast layer 3 IP address. If I don't know your MAC address, if I'm the source host H1 and I don't know your MAC address, I'll send out that broadcast address resolution protocol broadcast that says, calling all stations, if your IP address is 192.168.1.200, please tell me what your MAC address is. That's 0007E942AC28. Host H1 needs to know that before he can encapsulate the data and send it to him. So IP version 4 uses address resolution protocol, and IP version 6 uses a similar protocol known as neighbor discovery. The source MAC address is always a unicast. Now broadcast. This is the broadcast, two most common sources for broadcast in networks today. ARP requests. We're constantly sending a sprinkling of ARP requests throughout the day because a workstation will only hold on to this link, this relationship between the layer 2 IP address, layer 2 MAC address, layer 3 IP address. You'll only hold on to it for about 3 minutes, because you could have a laptop computer and you could walk to the library and you would be on a different network, and your MAC address would be the same physically, but you would be on a different layer 3 network address. So it expires after a few moments. So if I haven't logged into the workstation and I came back from lunch, I haven't used it for an hour, then I'll send an ARP request, I'll log into that server again, I'll do my afternoon work. So a broadcast address is a special address. It's not memorized by the MAC address tables of switches. It's all ones. In binary, 1111, which is 15 in decimal, is F. So F, 12 Fs is 48 binary ones. It's a special address. Ethernet switches have a special way of responding to any time that they receive a destination address of the broadcast. They flooded out all the other ports. Not the port it came in on, not the incoming port, because it already came into the incoming port. But they flooded out all the other ports, because if you're doing an ARP request, you don't know what port he's plugged into. You got to send it to all the ports. The other common source of broadcasts is the DHCP request. When a workstation boots up and he needs to send out a broadcast request to the DHCP server to grant him an IP address to use on the network, that's initially sent out in the form of broadcast. So switches are compelled to flood this to everyone else. Our switch in the upper part of the blue triangle has flooded this request to everybody else on the network. Routers do not forward broadcasts. So broadcasts are filtered and only in the individual local area network, because you don't do an ARP request to people outside of your network. You only do it because you're trying to find the MAC address of the line printer so you can print your document. Multicast MAC addresses are used for special purposes like spanning tree protocol. We'll get that in a later course. Some routing protocols use multicast to send routing table updates to other routers. It's kinder and gentler than a broadcast. Is like these people that post on forums, all capital letters. It's kind of like they're shouting. Multicast is kinder and gentler. It's, well, they're just going to capitalize the first word of every sentence. So there are some special reserved 48-bit MAC addresses that are used for multicasting. There's one reserved address for OSPF. There's one for spanning tree protocol. And it's flooded out all the ports like the broadcast is, but the workstations are programmed to just ignore them. In this case, the destination host group was the 3 servers in the upper right-hand part of the corner. And because he used that particular address, they paid attention to it, and they didn't bother the operating system. They didn't slow it down. Now let's look at the MAC address table. Inside of an Ethernet switch is a special type of physical memory called content addressable memory. It's kind of similar to RAM, but it's called CAM because it's super fast lookups for numbers. So they use it in switches. So a layer 2 Ethernet switch uses layer 2 MAC addresses to make his forwarding decision. He really doesn't care. The switch itself really doesn't care about the upper layer data being carried in the Ethernet frame. It could be an IP version 4 packet, or it could be anything. He doesn't care. He doesn't pay attention to it. He's going to make his forwarding decision just based upon the layer 2 destination MAC address. So every time an Ethernet frame is sent out by your PCA and it goes into port 6 of your switch 1 is going to, first of all, he's going to look at that source address and he's going to add it to his MAC address table. If it's already in there, he's going to update the timer. It's about a 5-minute timer. So switches really do 2 things. We used to call them learning bridges. The switches used to be called bridges. So switches learn or relearn the source address and they update the MAC address table. And the reason they have to update the MAC address table is the second thing they do is choose where to forward this Ethernet frame to the destination. They're going to look at that destination address. They're going to look in the MAC address table and they say, oh, I have this MAC address table. Oh, he's on port number 18. I'll send it out port number 18. If he doesn't find any entries in the MAC address table, he'll treat it like a broadcast. He'll flood it out every port. We call that an unknown unicast. Now, when you first turn on a switch, the MAC address table is empty. Or if you do a reload on the switch, it's initialized, it's empty. And he'll start learning again right away. And this is the mechanism that Ethernet switches use to make their forwarding decision. So the first step, learn. Examine the source MAC address, learn it, put it in the MAC address table. If it's already in the MAC address table, update the timer. If it's not in there, put it in there and start the timer. Now we need to do the second process. The first process was learning the destination, learning the location of the source machine. I know who you are and where you live. You're PCA and you're plugged into port number 6 at switch 1. Now I'm going to look at the destination address. Oh, you're trying to ping PCB, who's plugged into port 18 of a second switch. So let's find that destination MAC address and make the forwarding decision and send it along. If it's a unicast and I've learned the destination MAC address, it's in my MAC address table, I'm very efficiently going to send it only to that other switch, to that second port, so it can be forwarded to that device. Now, if it's a broadcast or a multicast, I am compelled to flood it all the other ports, except the one port it came in on. Okay, so here's our unknown unicast thing. If he looks in the table and he doesn't see the destination address on the table, he hasn't learned it yet. Maybe I'm pinging somebody and they haven't been doing anything for 5 minutes, so they're not in any tables. As soon as he replies to me, then his address will be updated. So this combination of the switch port being updated and the ARP request process is what commonly causes the first 1 or 2 pings to fail. You'll get no reply at all. And then all of a sudden you'll start working. If you ping it again immediately, it'll keep working great until the 3 minutes or 5 minutes runs out and all the caches expire and they get forgotten. So switches can filter frames and only send them out to a single port. So if workstation A is talking to workstation D, in this case, in the MAC address table, he's already learned the exact MAC address of host A and host D. So he doesn't have to send the data to the other ports B and D. He only needs to send it to ports 1 and 4. So ports B and C hear complete silence. They can actually have their own private conversation, and they'd be able to use the full capability of their wires. So this is, hubs are like the party line in the country. Everybody has to share one telephone connection. Switches are like private telephone lines. Okay, I've got a line, the teenager's got a line. We can both talk on our separate lines and we won't be able to interfere with or hear each other. Now, there are some hardware tricks that the Cisco hardware engineers have come up with. If we look at this, learning process. An Ethernet frame starts to flow into PCA's Ethernet frame starts to flow into port 6 of switch 1, bit by bit by bit. Slowly he turns, slowly it goes in there bit by bit. And switch 1 receives the entire Ethernet frame and checks to make sure the CRC is good, it's not a bad frame. And then he goes and looks in the MAC address table and determines where he's supposed to forward this frame to. That's called store and forward switching because he reads in the entire frame and then he forwards it according to what's in the MAC address table. Cut-through switching is, remember I mentioned before that the destination address, MAC address, was the very first part of an Ethernet frame, the first unique part of every Ethernet frame. That means that I can go ahead and make my forwarding decision after the first 48 bits. I don't have to wait for the entire frame to be read. So I can read the destination address in 48 bit times instead of 1500 bytes and go ahead and start forwarding that frame out the destination port even before the entire frame has been received. So that can really speed up the performance of a network. So that's a disadvantage in the sense that if the frame's going to have errors, I'm carefully forwarding garbage onto another network. However, the advantage is I can have super fast performance. If I'm doing any type of quality of service or I want fewer errors on my network, I'm not going to use cut-through switching. I'm going to use store and forward switching. Now, Cisco used to program all their switches for cut-through switching so they could claim super fast performance. They changed their minds. They became a little more conservative. So now all Cisco switches come by default set for store and forward, but you can set it through cut-through switching if you want to. So if you're doing something like voice over IP, something like that, where we're doing quality of service, where we have to examine each frame and put someone at the head of the line, the telephone has to go at the head of the line because you can't have any latency with telephone conversations. Can't do cut-through, got to do store and forward only. There's two types of cut-through switching. Fast forward switching is the lowest latency, the least delay, because it's immediately after the first 48 bits of that destination address are read in, he's going to start forwarding that frame up the destination port. So if the packet has errors in it, we're going to relay the errors. That's okay. The destination NIC card will determine the error of the CRC. He'll throw it away. The compromise between store and forward is the most conservative. Fast forward switching is the most liberal. The centrist view is fragment free. It turns out that if there's going to be an error in an Ethernet, it's almost always within the first 64 bytes. It's a collision fragment or there's an error, we're going to know within the first 64 bytes. So in fragment free switching, instead of waiting just 48 bit times, I wait 64 byte times. That's about 12 or 16 times more time. And if I receive the first 64 bytes of the 1500 it could be, and I see no errors, then I'll start forwarding up the destination port. So this means I won't be relaying so many possible errors. So you can choose to be super fast or super slow or in the middle. But by default, Cisco switches now are programmed for store and forward. Now for the hub, there was no memory. Hubs were just, they were synchronous. Any bit that came in the first port, it was immediately flooded out to the other ports. But switches have to, form a unique virtual circuit between port 6 of your PCA and port 18 of your PCB when you're sending traffic back and forth. So they have memory buffers in them to save the information. For example, what if 20 people are trying to log into the server at the same time? On a hub, that would be lost. There would be collisions. But on a switch, the memory buffers will hold, the guy in switch 1 gets in first, his data is forwarded first, and the guys in ports 2 through 19 They're going to be held in memory buffers and released one at a time, and the server will eventually log everybody in. So there's two ways we can set up the memory for this. We can set up port-based memory where there's dedicated chip for every port. That way, if one port is busy, it can't slow down another port. Or you can have shared memory where there's a common chips and it's shared by all the ports. So there's advantages and disadvantages to each one of them. And the more common we use is shared memory. It's a little bit lower cost to the manufacturer. So you can go and buy that $10 5-port, 8-port switch from an office supply store. It's going to be using shared memory. And keep in mind that if let's say your workstations are attached like in the classroom at 1 gigabit speed and the server is attached with 10 gigabit speed, you can't use any fast forward because they're different speeds. It must be store the entire frame at 1 gigabit and then shoot it out to the server at 10 gigabit. Then when the server sends its login back to you at 10 gigabit, it needs to be slowed down to the 1 gigabit that you can comprehend. So anytime different speeds are involved, it has to be store and forward. Okay, duplex settings. It used to be a problem 15 years ago that when I plugged, say, 2 switches together, switch 1, switch 2, and one of the switches would decide that port 1 of switch 1 that goes to port 1 of switch 2, switch 1 decides it's going to be half duplex, and switch 2 decides it's going to be full duplex. Oh, well, if I'm full duplex mode, I can send and receive anytime I want to. Switch 2 says I can send whenever I want to. Switch 1 says, oh, I'm only half duplex. I'm trying to transmit, and I hear your data. There must be a collision occurring. So this caused lots of errors between the two different switches. There's an auto negotiation hardware circuit feature that's been built into almost all Ethernet interfaces now since about 15 years ago that will automatically match up if they're either going to be both half duplex or they're going to be both full duplex. If they be both 1 gigabit or both 10 gigabit, whatever speed they can be. And that way they're going to get the best possible connection. If you're using 2 different vendors of devices, you might still see this problem crop up. So my S1 is a Cisco switch, my S2 is a Nortel switch, and they can't do the half duplex properly. Maybe one's half duplex, one full duplex. I can go into the iOS command line. I can manually force them to both be half duplex or force both of them to be full duplex. Now, please note that if it's gigabit or faster, there's no such thing as half duplex. Now, with our switches that we have in the lab, it has 24 fast Ethernet ports and 2 gigabit ports. So it is possible with the 100 megabit fast Ethernet ports that you can have one half duplex and one full duplex, and you can get errors. So whenever the half duplex switch, whenever the full duplex switch says I can send whenever I want to, the half duplex switch says I can only send when there's no data being sent. And what are all these collisions that are occurring? Because the full duplex switch is like the Three Stooges poking each other's eyes out. He's sending data whenever he wants to. He doesn't listen for it. He says, must be a full duplex connection. He can send and receive at the same time. So if you have a problem, simply manually configure both switch ports to be full duplex will give you the best performance. Oh, the last thing is auto MDIX. The cable types that we have to understand for CCNA objectives are a straight-through cable, a crossover cable, and then that baby blue rollover cable that you use with a console port. So Ethernet ports, you only plug in straight-through cables or crossover cables. So it used to be that if you plug 2 like devices together, like 2 PCs or 2 switches, or in my case, when I first got my cable modem in 1995, they had to plug a crossover cable between the cable modem and my PC. Otherwise, it wouldn't have operated properly. But these days, since about 15 years now, auto MDIX is a feature that no matter when you plug devices together, if you should have used a crossover cable and you use a straight-through cable, or you should have used a straight-through cable, use a crossover cable, the transistors will automatically gussy up the connection for you and make it work properly. So almost all devices have this feature now. The last batch of routers that we had in the classroom, there was not auto MDIX on the router port, so if you plug 2 routers together, you had to use a rollover cable. But the routers we have now, all of the equipment that's in the lab now, all the routers, all the switches, all the host PCs, or auto MDIX. And you can go to the command prompt, iOS command prompt, and change this if you want to. Okay, hold on, I'm gonna stop recording. I think we've covered everything.